questions of statistical inference. Most often we're going to deal with means and proportions. Those are going to be kind of our focus. So today we're going to go through section 7.2. We're going to talk about sample proportions. So when we have a sampling distribution involving proportions, what are things we can do? Next week we'll talk about what we can do with sample means. Okay? So with sample proportions, some things to note. When we have a sampling distribution with sample proportions, the shape. Now, sampling distributions can come in lots of different shapes, depending on the sample size and things of that nature. They could be skewed, they could be symmetric. However, the ones we're going to focus on are the ones that come out to be symmetric. So when we're talking shape, what's going to be happening is our sampling distribution for p hat. So in this case, our sample proportions. We can approximate it with the normal curve. Like I said, Chapter 2 material is not going away anytime soon. You are still going to be working with the normal distribution and calculating percentages and probabilities from that. So we're going to approximate using a normal curve. Now, when we can and cannot use a normal curve will it depend entirely on the sample size and the population proportion. Okay? So there's going to be both aspects that we have to take a look at in order to decide whether we can use the normal curve or not for our calculations. So, while a sampling distribution can take on a symmetric or skewed value, we are going to try to focus more on the ones that are symmetric and the ones that we're able to use a normal distribution to calculate different probabilities. The center of a sampling distribution. So the mean for the sampling distribution of a sample proportion is always going to be the population proportion. Now some things in this one. Notation. When they want the mean of a sampling distribution, they're going to use mu sub p hat. So mu of p hat, because we're looking at a sampling distribution for proportions. So what that notation literally means in English is the mean of our sample proportions. So if we have our sample proportion, and under the right conditions, when we can use a normal curve, our population proportion will be the mean. And that's because proportions are unbiased estimators. What did it mean to be an unbiased estimator?
It can be used to estimate the overall population.
Kind of. If a value, if a statistic was an unbiased estimator, what did it mean? It was equal to or just about equal to the actual parameter value, right? Now, what was the other aspect of it? Because in this case, we're already saying that the mean of our sampling distribution is equal to the parameter mean, or the parameter value. So what was the other aspect of an unbiased estimator that was important? Think about the process we use to create a sampling distribution. We go out and take a sample, we get a result that we record, and then we go out and get another sample, we get a result, and we record. If it's an unbiased estimator, what should those samples be coming back as? How would they relate to the actual parameter value? Should be fairly close to it. What else? We should be getting about an equal number of values that are above the true value and some that are below the true value. If our statistic was a biased estimator, most would be coming back too low or most would be coming back too high. So when it's unbiased, the center of the distribution is going to match the parameter value, and when we take our samples, some will be high, some will be low, but there should be an approximately equal amount in each direction. Okay? So when we talk about the center of our distribution, the main thing is the notation. And then with that also, knowing that the parameter value is the mean of the distribution. For spread, since we're talking mean, our spread will be the standard deviation of the distribution. So again, some notation. We're talking about a standard deviation, so we're going to use that lowercase sigma sub p hat, so the standard deviation of our sample proportion. Now some things to note about standard deviation. It will decrease as sample size increases. So n here is representing sample size. Anytime you see n, from here on we're talking the sample size. So if we increase the sample size, our standard deviation will automatically decrease. The other thing we're going to say for now is that the value of standard deviation will be dependent on the values of the sample size and the population proportion. And we're going to talk about how to calculate it here in a second. So for shape, we're going to focus on sampling distributions that have an approximately normal distribution. The center will be centered at the population proportion value. And for spread, we're going to be calculating based on the population proportion and sample size. Okay? So, when we work with proportions, and we want to set up our sampling distribution, knowing the mean will automatically give us the standard deviation. So when we're working with a sampling distribution for proportions, and it's going to be important that you distinguish because, like I said, next week we're going to talk about sampling distributions for means, which means at some point they're just going to be throwing sampling distributions at you. You need to know what you're dealing with. Proportions have a set of equations and properties that we can work with. Means have a set of equations and properties that we can work with. And so if we don't know which one we're working with, we don't know what set we're going to be dealing with. So the mean of your distribution, we already know, is the population proportion. The standard deviation will always be calculated by taking the square root of the population proportion times Q. What does Q represent? And we had P and Q. How did P and Q relate? They were opposites. What's the actual word we use though? So it's the C. Complements. Okay, so P and Q are complements of each other. So if our population proportion was 70%, the mean of our sampling distribution would be 70%. The standard deviation would be the square root of 70% for P times 30% for Q. So they're going to be complements. They always have to add up to 1. And then we would divide by whatever the sample size is. Okay? So these are two formulas I would suggest you memorize. Now these will be given, I believe, in the formula packet. However, if you're always flipping back and forth between the test and the packet, it's going to take time away from answering questions. These are pretty simple to remember. The mean of the distribution is always the population proportion. The standard deviation is P times Q over N, all inside the square root. Okay? So, when we talk about our distribution then, like we said, we're going to be talking about ones that are hopefully able to be approximated with the normal distribution. So the normal distribution takes two arguments, the mean and the standard deviation. So our mean is the population proportion, standard deviation is the formula we just discussed. Okay? So, for instance, if I gave you a situation where they said the population proportion was 65%, And we took a sample of 150 people at a time. Okay? If I were to set up my distribution, so if I were going to set up my distribution according to the model here, what would my mean be? 0.65. So the mean would be 0.65. What would my standard deviation be? Let's just write out in formula. So I'd have the square root of 0.65 times 0.35 divided by 150. Okay? So on the problems that you'll be getting, one of the main or very important things that you need to be able to do is this first step. Set up your distribution. What is your mean? What is your standard deviation? So that's identifying that the population proportion is the mean and the standard deviation is given by the formula here. Now, when you're doing these types of problems, the absolute best way to do it, the most accurate way, is to keep this in this format throughout. However, if you're writing all of that out every time, it can sometimes be very cumbersome. It can become kind of a pain or a hassle. So if you're going to plug this into your calculator, so if you plug this in your calculator and get an approximation, try to keep at least 3 decimal places. Okay, the more you keep, the better, the more accurate it's going to be, but try to keep at least 3 to give yourself the most accurate possibility. Okay, so just some things to note there. The other thing, make sure when you plug this in your calculator, one of the biggest things people mess up is when they plug in the square root, they do the 0.65 times the 0.35, and then when they divide by the 150, that 150 sometimes gets left outside the radical. So a way to do this to make sure you don't mess up is do all of the inside first. So take 0.65 times 0.35 divided by 150, and then take the square root of that result. So in your calculator, that would just be taking the square root of the answer and get the actual value. Okay? So just some things to note there so that you don't mess up order of operations. You okay with this so far? So identifying mean, identifying standard deviation, we're okay? All right? So basically what will happen then, when we're able to use a normal distribution for our approximation, this is what it's going to look like. Now this is not anything new. This is the exact same shape. It's the exact same model that we used before. The only difference is, instead of simply saying 1 standard deviation, 2 standard deviations, 3, it just has the formula in it. So when you draw your normal distribution, your population proportion is going to go where your mean is, and then if you add 1 standard deviation, add 2 standard deviations, add 3, you get to your different spots, or subtract 1, subtract 2, and so on. Okay? Another way of looking at it, if we're looking at our distribution, the x-axis gives us a list of our possible sample proportions. Our mean, still located at the population proportion, standard deviation calculated in the book. If you look in the book, we'll use this formula here. So if you want that formula instead of P times Q, you could use that to remind yourself that they're complements of each other. But it's the same normal distribution we've been dealing with since chapter 2. Okay? So, if we're going to use a normal distribution for approximation, there are some assumptions and conditions we have to verify before we're allowed to proceed. So in some cases, our distribution might come back symmetric. We might be okay, or might justify using a normal approximation already. Other times, our original distribution might be skewed, but under the right conditions, we might be able to force it into a normal distribution. So, when we're using this model, a couple assumptions that you need to justify or verify. And with these assumptions, the conditions we're going to talk about on the next slide essentially take care of these, but they're ones that you do want to think about as you're going through the process here. So the first thing you have to verify is that you have independent sampled values. So whatever you happen to be sampling, the individuals in your study, the sampled values must be independent of one another. So we always have to have that assumption of independence. The second assumption is called the sample size assumption, and that says that the sample size, or N, must be large enough. Okay? So these are things to think about. Now we're going to talk about some conditions here. These conditions, if they're all met, will account for these assumptions. They're going to take care of these assumptions we need to be making. Okay? So, while these are important to think about, they're going to come along when you check the conditions. So if you can verify that the conditions are all met, then these are going to be good to go. So the conditions, these are ones you have to memorize. They'll not be given to you. You have to know them. When you're working with a sampling distribution for proportions, the first condition that must be met in order to use a normal distribution is the randomization condition. So the randomization condition says the sample we collected was a simple random sample of the population. So you need to verify that somewhere they used randomization in the sampling process. Okay? With that, we need to verify the second condition, which is called the 10% condition. The 10% condition is the same as what we had before when we talked about simulations and probabilities with the binomial and geometric models. So the 10% condition says the sample size must be no larger than 10% of the population. Now, the 10% condition somewhat contradicts an idea we talked about yesterday, specifically when we talked about spread. What did we say when we were talking about spread yesterday? The larger the sample, the better, right? But this 10% condition is almost somewhat contradicting that. It's saying that we can't take a sample larger than 10% of our population, right? So when we look at this, the reason that this isn't too big of a deal when we're talking about large samples is that most of the time our population of interest is so large, we're not going to be taking a sample large enough to even come close to this 10%. Okay? So this 10% condition is kind of a formality. We just need to make sure that for smaller populations we check it. If we were talking about like all U.S. households or all U.S. adults or something like that, there's no sample we could take that would come close to the 10%. Okay? But if we're talking about a sample or a population of like this high school, so if there are 1,500 kids in the high school, what's the largest our sample could be before we violate this condition? 150. Okay? So you have to kind of balance the idea that the larger the sample, the better, with this 10% condition. We can't take more than 10% of the population. Now, if these two conditions are met, then that independence assumption is automatically taken care of. Randomization and 10% guarantee independence, or at the very least, it guarantees that the probabilities we're dealing with won't change as we sample individual after individual. Okay? The last condition takes care of the large enough, or the sample size condition. So the sample size condition said the sample has to be large enough. Well, what does that mean? It means this. The success-fail condition has to be met. So the sample size has to be large enough so that when we take the sample size times our mean times our population proportion, we get at least 10. And when we take the sample size times the complement of our population proportion, we get at least 10. So remember, n times p, that was like the number of successes we expect in a sample. N times q was the number of fails we expected in a sample. So our sample size has to be large enough that we can expect 10 successes and 10 fails. If that condition is violated, we are not able to necessarily use the normal distribution for an approximation.
Is it when they're added together, n times p plus n times q?
Nope, separate.
Okay.
Yep, so if you want to write next to this, what this really is saying is n times p has to be greater than or equal to 10, and n times q has to be greater than or equal to 10. Okay? So, when you're working with these types of problems, one of the things that you have to do with each problem, if you are going to be using a normal distribution to work with it, you need to verify these conditions first. So you need to actually write out randomization, and you need to state where they tell you a random sample was included or involved. Then you need to write 10% condition, and you need to verify that the sample is less than 10% of your population. And then you have your success fail, and you need to show that n times p is greater than or equal to 10, and n times q is greater than or equal to 10. So each problem you do where you're going to use the normal distribution, you have to verify these conditions. That is not something you can leave off. On a quiz or a test, you will lose points if you don't have the conditions verified. Okay? So you have to mention these three. That's why you have to memorize them and know what you're doing for each one. Are we okay with those? Okay? So, before we get to an example here, this is not something you need to write down. This is just something to kind of remind myself to tell you. Sampling distribution models. So when we're looking at these sampling distributions, the purpose is, in the real world, there's only so much we can do. Okay? Sometimes our population is so large, we're never going to be able to actually find the value that we need for our population. These sampling distributions, their properties and characteristics allow us to bridge what we can do in the real world with what we can do in the statistics world. So this is the information we can get from the real world, but it has its limits. What we can do with these sampling distributions is move it to this world of statistics where we can actually expand and generalize our findings. We can take what we get from a sample and expand it to a population. So that's the main purpose of these sampling distributions and the ideas that we're discussing over the course of this semester. Okay? So, here's the example I want to go through. The CDC reports that 22% of 18-year-old women in the United States have a BMI of 25 or more, a value considered by the National Heart, Lung, and Blood Institute to be associated with increased health risk. As part of a routine health check at a large college, the physical education department usually requires students to come in and be measured and weighed. This year, the department decided to try out a self-report system. It asked 200 randomly selected female students to report their heights and weights. Only 31 of these students had BMIs greater than 25. So is this proportion of high BMI students unusually small? Okay, so what we're trying to verify is how unusual this particular sample is. Okay, so some things to note here. What we're looking at is a proportion problem. We're looking at whether they were above 25 or not. Okay, so they fit into one category or another, which means we can only calculate proportions. So, the things you need to be able to look at in the problem and pull out as pertinent information. First, they should be giving you a population value. So what is our population proportion? 22%. Okay? So the population value, the CDC has conducted studies, or enough of a study that they say the population value is 22%. Okay? That's one. You have to know what the population value is. Okay? The next thing you want to look for would be the sample value. So the population value is 22%. We want to know what our sample proportion was. So the next thing we look for is p-hat. So if we look at the problem, we took a sample of 200 randomly selected students, 31 of which had BMIs greater than 25. So our sample proportion would be what? It would be 31 out of 200, which would be, what is it? 0.155. Okay? So the population value, population proportion, 22%. At this large university, they're estimating that it's actually 0.155. Okay? So we want to determine if this is an unusual value or not. Well, the only way to do that is to figure out what is the probability. So if this is the correct proportion of female students with a BMI of 25 or higher, if that's correct, what is the probability that we find a sample proportion this low or lower? So what's the probability that we find our value if that 22% is correct? Does everybody understand that question? Because that's the entire basis of what we're doing here, is understanding exactly what we're trying to calculate. So we're trying to calculate a probability based on the 22% assumption. So we're okay with that? Now, with this then, the only way we're able to calculate the probability is if we have a normal distribution to work with. So once we have identified the pertinent pieces of information, so we have population proportion, sample proportion, what's our sample size? 200. So that's another thing we probably want to keep track of. Okay? So we need to verify that we have a normal distribution. How do we verify that it's normally distributed? The three conditions. So at this point, we'd have to go through and verify those three conditions. So condition one was randomization. So did we have randomization utilized in the sampling process? Yeah, and we know that because they say randomly selected. So on this, if you're doing the homework or on a quiz or a test, all you have to do is tell me where they said something about randomization. Okay? So they actually said 200 randomly selected female students. Now, there are times where they might not specifically mention random in the problem. What you would have to do then, if they don't specifically say they were randomly selected, you would have to make an assumption. Randomization is supposed to give us a representative sample, right? That's the whole point of it. So if they don't mention randomization specifically in the problem, you would simply say for this, assume samples represented. That at least tells people we don't know what type of sampling they used, so when we find our answer, it may or may not be right depending on how they did it. We're assuming they did it correctly so that we can proceed. Does that kind of make sense? Okay, so they were randomly selected. The second condition is the 10% condition. So the 10% says that 200 needs to be less than 10% of our population. So a couple different ways of thinking about this. If we're talking about a large university here, right? If I had a sample of 200, that would be 10% of what? 2,000. Is it easy to assume, or can we assume that in a large university they have more than 2,000 female students? Yes, a large university is going to have more than 2,000 students, okay? So you could either write that out, so take like the 200 times 10, so 2,000 is less than the amount of female students a large university would have, or you can simply write something to the effect that 200 should be less than 10% of all female students at a large university. Okay? So you do have to make some sort of note that the sample we took should be less than 10% of the total. Okay? Then, the last condition was success fail. Okay? So with the success fail, we needed to do what? Yeah, we need to do n times p. So if I do n times p, that would be 200 times 0.22. Why not 0.155? That's a proportion. Because that's the sample proportion. We need to verify according to the population proportion. Okay? This is what we're assuming to be true, so this is what we're going to use. Okay? So we take 200 times 0.22. Someone do that real quick. 44. Is 44 greater than or equal to 10? Yes, it is. So now we check NQ. So for NQ, we could actually calculate it out, take 200 times 0.78, but if we know we're going to get 44 successes, how many fails should we get? 156, right? We have to have the complement. Okay? So the other way you can do it is take your total sample size minus the MP. That's going to give you your NQ. So a couple different ways to calculate. So 44 and 156, both greater than or equal to 10. We good there? So now we know we can use our normal distribution. So now that we know we can proceed, we have a normal distribution with a mean of 0.22. Now for our standard deviation, we need to calculate that real quick. So the standard deviation would be the square root of 0.22 times 0.78 divided by 200. So if someone would do that in their calculator real quick, 0.029 what? 3. Okay. So try to keep 3 significant figures, 3 actual values, not the 0 placeholders when you're doing these. Okay. So 0.0293. So we can use that as an approximation. So here's where our normal distribution calculations kick in. If I want to use my normal distribution for probability, what do I have to calculate first? Z-score. So if I need a Z-score, we take the value in question, which is our sample proportion, so something you may want to write down. We're using just different notation. Before it was x minus mu over sigma. Since we're dealing with a sampling proportion specifically, I'll write this on the board over here so it's more clear. So Z is the sample proportion minus the population proportion over the standard deviation of our sample distribution. Okay? So, for this particular problem, that would be 0.155 minus 0.22 divided by 0.0293. Everyone with me there? So, what do we get when we do that? Negative 2.218, so we can go to 22. So remember with z-scores, 2 decimal places, especially if you're using the table, okay? So we got negative 2.22, so that's our z-score. What we're looking for here, our question was what's the probability of getting a z-score this low or lower? So we're looking at less than. So one way would be to look negative 2.22 up on the table, take the value from the table. The other way is on your calculator. So let's do it on the calculator here. Let's refresh your memories on that. So if you want to run through it, I would grab your calculator real quick. You will always have access to the tables on quizzes, tests. If you're doing your homework, the table's always in the back of your book, or if you took a picture of it with your phone, whatever. So you always have the table if that's the method you choose, but the calculator's an option as well. So if we want to calculate this probability, that we're going to go less than negative 2.22, we're going to go to second vars. So get into our distribution menu. Option number 2, I believe it is, should say normal CDF, right? So you want to choose normal CDF. And then for most of you, it's going to give you like a menu, right? Low bound or high bound or something like that. Others of you might just get the function itself. Like that, okay? So if you get the function itself, you're going to type in kind of in the order that we're going to talk about right now. So the low bound, if we're looking for z less than negative 2.22, that means we want to go all the way to negative infinity if we can, right? So in your calculator, the way to do that is just pick a really large negative number. One of the biggest numbers your calculator will accept would be negative 1 e to the 99. That e button is the key, right? It's like second comma or something like that, right above the 7. So if you go negative 1, second comma, 99, that's going to be your low bound. Most of you, if you have the menu that defaults to that, for the lower bound, so you might not have to type that in. The next thing then is the higher bound, so where do we want to stop? In this case, we want to stop at negative 2.22. And then, what else does it ask for? Mean and standard deviation, right? So since we standardized, mean is 0, standard deviation is 1. For you guys, it should already be 0 and 1. Never change that. Okay? So, when you put that in, what do we end up with as a value? 0.013. Okay? So, now we're going to think about what this probability means. 0.013. So listen carefully, guys, because this is important. This is going to lead us into everything else we do here. So this 0.013 says if our population value is 22%, so if 22% of all female students in the U.S., so all 18-year-old women in the U.S. have a BMI of 25 or higher, the likelihood that we would gather a sample with only 15.5% is only a 1.3 chance. So if 22% is correct, the probability of getting our value, or in this case smaller, would be 1.3%. So would we consider this an unusually small proportion? Yes, we would. Why do you suppose it's so unusually small? It's self-reported. If someone asks you your weight, what do you generally do? You might drop a couple pounds, right? So normally, you're not going to say what your true weight is. You're going to drop it a little bit because, for whatever reason, lighter seems to be better, right? So, if you're doing a self-report system, that might be a problem with their program. So those are the kinds of things you look at. Since this is an unusually small value, we need to figure out why is our university so much smaller, okay? Maybe, and there's options, maybe this 22% is not true, okay? So maybe the CDC wasn't correct in their calculations. Or, because they did a self-report system, maybe that was the issue. If they actually did the same setting, and they did 200 randomly selected people, and actually physically measured them, maybe their proportion would jump up into a more reasonable range. Okay? But those are the kinds of things we're looking at. So, when you're given a problem like this, and you're talking about whether a value is unusual or not, this is the process. So list out your pertinent information, population proportion, sample size. Run your 3 conditions. Now, if those 3 conditions aren't met, there's nothing to do. If they're not met, you can't do a normal distribution. So whenever you run into those, that's why those conditions are so important. It saves you time and work. If they are met, you need to state your distribution with the correct mean and standard deviation, calculate your z-score, and then calculate your probability. This one happened to be a less than, okay? And we knew we wanted less than because we were talking about a value less than our mean. If our value was higher than our mean, we might have chosen the probability that it was greater than, right? And then work with that. So you just got to kind of keep those things in mind.
Greater than in your calculator, just switch those things out.
Yep, so if this was greater than, like if we wanted to do a greater than negative 2.22, we'd still do normal CDF. But now if I'm talking greater than, my lower bound is actually going to be the negative 2.22. My upper bound, I'm going to change to positive 1 e to the 99. And then we still leave 0 as the mean, 1 as the standard deviation. So yeah, if you're going to do a greater than, you do that. Now, where the calculator has an advantage over the table, because those are fairly simple to do, like looking up on the table and just calculating, where the calculator has an advantage is if you're doing a range of values. If you're going from one z-score to another, you can type the lower z-score and the higher z-score in. It's going to do all the subtraction for you, so you don't have to do all that extra work. Okay, but otherwise, either way is going to give you the same answer. All right, so here's your assignment. Now this is going to be a little bit longer assignment, okay? The problems are a little bit longer than the problems we had last semester. So that's one thing to kind of keep in mind here, but